briefly talked about today. So the point that I was making today was specifically how if you took two aldehydes that have alpha enolizable protons, you can expect four products. So if I consider acetaldehyde, we talked about how acetaldehyde can react with itself to produce its dimer, and recognize if this is a C2, the product is also C4. In the case of propanol here, which is a C3 carbon, if it dimerizes, it will produce a C6. 1, 2, 3, 4, 5, 6. Okay? Now, the other part that I want you guys to recognize is that, again, the bond that's being formed here is the bond between this carbon, which is alpha to the carbonyl, reacting with this carbon, which is the beta carbon. And again, if you permit me to remind you about the self-condensation of acetaldehyde, this alpha carbon is the nucleophile that's formed from the enolate by deprotonation of that position. And that enolate will react with the carbon of the carbonyl as electrophilic center. So the alpha carbon, once again, is always nucleophilic, and the beta carbon that has this OH here is always coming from the electrophile. So in all of these cases, you can see that I have an alpha-beta bond here. Alpha nucleophile, beta electrophile, alpha nucleophile, beta electrophile. And then in these iterations, again, here is a carbonyl, so that's my alpha, that must be my enolate reacting with the beta carbon, which is my electrophile in this case. So I have structurally up to 4 of them that I can form. So again, as I pointed out to you, this would lead to a huge mess. It would be synthetically not very good to do, because you would have to basically purify up to 4 compounds, which is not economically favorable. So what I want to talk to you today about is how one can actually do practical cross-aldals. And so what is a practical cross-aldol? What I have here is the following. So recognize I have 2 molecules, one shown in magenta and the other one shown in blue. Now the one in blue here has alpha hydrogens. Okay, so here's my carbonyl, and recognize alpha to the carbonyl is this methylene. I can deprotonate this, but if you look at the magenta one here, this is benzaldehyde, and benzaldehyde has a carbonyl, but adjacent to this carbonyl is this benzene ring, which does not have an alpha proton. So as a consequence, benzaldehyde cannot be a nucleophile in this reaction. It can only function as an electrophile. So if I treat propanol with strong base, sodium hydroxide here, I'm going to deprotonate this position, form the enolate, and this enolate is going to react with this carbonyl as an electrophile, okay, to give me this product, okay? Now, let's consider that with this one here, same idea. Here I have an alpha carbon. Again, this has no alpha hydrogens on it, so it's only electrophile. Again, it will do a condensation reaction where it will react with this and form this product, okay? Now, and here is the third case. Again, this has an alpha position, so I'm going to form the enolate, and finally, formaldehyde here, which only is 1 carbon, has no alpha carbon by default, so consequently, formaldehyde can only function as an electrophile. So if I deprotonate this, I can make this, and notice I make this alcohol here. Now recognize that I shared with you this today. Notice I get 3 different types of products here, right? 2 of these products goes directly to the alpha, beta, and saturated aldehyde. Whereas down here, this third product here gives you basically the beta hydroxyaldehyde. So could I eliminate this? Yes, I could, but I would have to do some work on it. What I share with you guys today is that whenever you have conjugation here, and the fact that in this molecule with benzaldehyde, I have a phenyl ring, this guy wants to eliminate beyond the beta hydroxy because the benzene ring is now conjugated with the C double bond H. So if you allow me, I'm going to show the mechanism for this first reaction with you. And I'm going to go and showcase the E1CB. And again, I'm going to try to exemplify why this reaction does not stop at the beta hydroxy, but goes all the way to the full condensation product, which is the alpha beta unsaturated system. So I'm going to stop sharing, and I'm going to try using the document camera. And give me 1 minute. Okay. So I apologize for the issue today. What I found was that I believe I needed to update my Zoom. And so I'm hoping the update fixed that issue. So I'm going to start off with propanol, because propanol has an alpha hydrogen that hydroxide can abstract a proton. So I'm specifically going to take one of these protons off this H, and this guy is going to form this enolate. So if you permit me, let me redraw this, showing the enolate here. Okay. So again, as I pointed out to you guys, why are we doing this? Well, enolates, the purpose of forming enolates is that they're nucleophiles. Okay. So now that I got this enolate, I'm going to redraw it here. Just to show the process. This guy can now react with benzaldehyde. So I'm going to draw benzaldehyde this way. And recognize that benzaldehyde has no alpha carbons. If you look at this carbon right here, it's bonded to a double bond, so that's 2 lines, that's 3 lines, that's 4 lines. There's no hydrogens here. So benzaldehyde is an example of an aldehyde with no alpha hydrogens. So consequently, benzaldehyde can only function as an electrophile in this reaction. So what I'm going to do now is showcase the arrow pushing for this reaction. I'm going to push this electron from the oxygen, and then I'm going to push this pi bond onto the carbon here, because the carbonyl is electrophilic, and push this guy up. Okay. And the result of that is I form an addition product. Oops. Put the oxygen in this way, and I'm still going to show the benzene ring. And I'm going to show the hydrogen. Okay? So that's the tetrahedral intermediate. And under these conditions of hydroxide, we generate water up here. Okay, so I have water in strong base that's going to function as my weak acid. So the next step is this alkoxide here is going to do an acid-base reaction with water to generate hydroxide, so regenerate the catalyst of hydroxide, and the alcohol. Okay. Now, what I was trying to say in class today is because I have the spinel ring, notice that right now, this carbonyl is not conjugated to anything. However, if I was to eliminate water, and let me draw in blue water here, this is what we're talking about in the E1CB mechanism, is I'm going to remove H2O, this hydrogen and this OH. In order to do that, what one is going to do is then take the hydroxide that's generated, okay, and I'm going to remove this blue proton from it, thus forming the enolate. So if you allow me, I'm going to move my arrows this way. I'm going to draw my carbon skeleton. That has nothing's changed. Only new part here is that I generate an enolate because I still have a carbonyl. This is a carbonyl, so this proton is still acidic, and so I have C minus here, and I have a carbon with an OH. And then I still have this carbon bonded to my phenyl ring. Okay? So this part is the first step to E1CB. So E1CB, first you generate the enolate at the alpha position, alpha to the carbonyl. And then the final step to make the product is, I'm going to do it this way, is elimination of hydroxide. Okay? And so once I form this guy can come in, and I have as a leaving group hydroxide. So the final product that's formed looks like this. So notice benzene now is conjugated. This phenyl ring is now conjugated with this double bond here, and this double bond is still attached to an aldehyde. Okay? So if you permit me here, the reason I have this driving force of not stopping here, oops, I apologize. So the reason that I have the driving force to eliminate this compound and go all the way to this product here is that this phenyl ring is conjugated with this double bond, and this double bond is conjugated with this carbonyl. So if I circle all atoms that are conjugated, that have resonance, it's all these atoms that I'm circling in blue. Okay, so this is a conjugated system. Whenever you have this type of conjugation, the result is that you do not stop at the beta hydroxyaldehyde. Okay? And I apologize, I should have lifted this up. So there we go. That's the entire mechanism. Okay, so again, just wanted to disclose that to you. It's a simple mechanism. In fact, I think there's a homework problem that I posted that actually asks you to do that. So I just did that problem for you guys, so you should be able to check your answer. Okay. So let me go back to the PowerPoint. And so now you can see that this phenyl ring is really conjugated with this system here. So this was the one that I just did on the document camera. This is very similar. Again, this phenyl ring would be conjugated with this alpha beta unsaturated double bond, and then this alpha beta saturated double bond is adjacent to this carbonyl of the aldehyde. Again, these are conjugated. Here you see that I stop here at the beta hydroxy because I have nothing that's pushing that conjugation. Okay. Another reaction that's practical is realizing what I shared with you today. Okay, you may have already seen this in context. What I said today is that the self-condensation of aldehydes goes very well. Okay. On the other hand, ketones don't want to form the aldol reaction, in particular with base. Okay. And the reason for that is, again, there's a lot of steric hindrance. So a practical Claisen reaction is one in which I can use a ketone that can only function as a nucleophile. Okay? So recognize one of the things you should have learned from Dr. Schwann when he talked about carbonyl chemistry of aldehydes and ketones is aldehydes are always more reactive than ketones. And a couple of reasons for this is one, methyl groups are electron donating. So an alkyl group is less electropositive than hydrogen, than this carbon here. So this is a better electrophile, whereas this is a poor electrophile based upon the fact that, again, alkyl groups are inductively electron donating. And also there's the other aspect that sterically, approach of a nucleophile is more hindered here because I have these two larger flanking methyl groups blocking this than just a carbon that only has one hydrogen. Okay, so as a consequence of this, I can do a Claisen-Schmidt reaction, which is a new type of aldyl, in which the nucleophile is a ketone, and specifically, I'm going to use, in order to get this reaction to run, I'm going to use an aldehyde that has no alpha protons. So again, benzaldehyde is chosen here because it has no alpha protons. So since it doesn't have any alpha protons, it's not a nucleophile. The magenta here is functioning as an electrophile. So again, my nucleophile that's generated here from the enolate is going to attack this carbon of the carbonyl to generate this one. And recognize again, this goes directly to the conjugate system because I have benzene ring here, conjugated with this double bond and the carbonyl. Okay, here's another example of that. Here I have a benzene ring on this side. So the only enolizable proton I have is this methyl group adjacent to the ketone carbonyl. So if I form the enolate is going to react with benzaldehyde here. Again, benzaldehyde has no alpha protons, and I get a reasonable yield of this cross aldyl, an 85% yield. All right. Again, I kind of did the mechanism, one of the mechanisms for you. I'm not going to go over this. Here's some examples that I took this specifically from your textbook from Sorrel. So here is a ketone, right? This ketone has a carbon with 3 methyl groups, so there's no alpha proton here. The only alpha proton I have is on this carbon. I have 3 hydrogens, so if I deprotonate this with a strong base, I'm going to make the enolate. The enolate can react with benzaldehyde. Again, notice I'm using benzaldehyde. Benzaldehyde, once again, has no alpha proton. It consequently can only function as the electrophile. So I'm going to attack this to this electrophile, and again, I get this alpha beta. Again, recognize what I shared with you earlier. Here I have a ketone that's alpha beta in the saturated system. I said the alpha position is always coming from the nucleophile. So this part here is this molecule in which I made this enolate. This part here, the beta carbon, is basically the benzaldehyde carbon that's lost water. Okay, here's another example of that. Here I have a methyl that has enolizable protons, and I can treat it with benzaldehyde that's only functional electrophile, and I form this conjugate system. In this molecule, you can see that I have a lot of conjugation. This is one of the molecules, if you were taking organic chemistry class in the summer that offered a lab, these molecules tend to be colored. They're conjugated. I'm going to finish off with a couple more slides, and then that will be it for today. So the last thing that I took from your textbook is how about an unsymmetric ketone with a Claisen-Schmidt. So again, benzaldehyde has no enolizable protons. Again, benzaldehyde is an electrophile because it doesn't have no enolizable proton. So consequently, I'm going to look at this ketone and say, okay, which is the proton that I can remove that's alpha to the carbonyl to generate an enolate? Well, it turns out this is unsymmetrical. I have this carbon which I can remove. That's an ethyl group, if you permit me, adjacent to this. And then I have a methyl group flanking this carbonyl, which generated a second enolate. So if I look at this, the major product is coming from this carbon in which I deprotonate this position and attack here to give me this guy here. Okay? On the other hand, if I abstract this proton, this guy is going to attack this position to give me this one. It turns out that the Claisen-Smith reaction with unsymmetrical ketones under thermodynamic conditions always proceeds where you abstract the proton that's least hindered. So again, today I talked about the difference of this position and this position. We said this is a kinetic enolate, this is a thermodynamic. In the Claisen-Smith reaction of unsymmetrical ketones, the reaction always proceeds to go by attack at the kinetic enolate, which is the protons that are least hindered. So this has a carbon with 3 hydrogens, whereas this carbon only has 2, and an alkyl group that makes it more hindered. So preferred pathway is this guy going by this process, and then I eliminate to generate this species. It turns out this is a very slow step here. This is much faster, so as soon as I form this, it goes back. So the reason we see this as a major product is because as soon as this is formed, it does a retroaldo. Okay, so a retroaldo is faster than elimination in this case. So the take-home message is, again, if you have an unsymmetrical ketone, it's always an attack at the less hindered site. All right, last thing, I promise. I also want to share with you the condensation with nitroalkanes. We talked about how nitro groups are potentially the alpha position nitro groups are highly acidic. Okay, so here is a nitro group, and here is the alpha carbon to that. If I deprotonate this with a base, notice I have resonance stabilization, just like I do with aldehydes. It turns out that this nitro group really enhances acidity. So whereas aldehydes and ketones have a pKa value of 20, the nitro group, notice how acidic they are. This is significantly more acidic than an aldehyde or ketone. It has a pKa value of 10, so it's very easy to protonate this. So notice one of the things I can do is I can take hydroxide with, this is nitromethane. Nitromethane will prefer to pull off this proton because it's the most acidic. This has a pKa of 10. And once I deprotonate this position, which forms a carbanion, that carbanion can function as a nucleophile and attack this carbonyl, which is electrophilic. So as soon as I form this is going to attack, and notice I eventually get the conjugated product, which is no different from the mechanism we did. Okay, what's the value of this? Well, if I wanted to reduce using catalytic hydrogenation, I basically have a mechanism of making an amine. Okay. Tomorrow I will talk about the cyclization reaction.